Okay, the last thing we need to talk about in this lecture number 3 is surface tension. This is a little bit of an aside. Viscosity was really the star of the show, but surface tension still plays an important role in a lot of fluid mechanics, especially small-scale problems, where instead of gravity being the dominant force of fluid mechanics, it's actually surface tension. Isn't that weird? Okay, so surface tension occurs at the intersection of a liquid and a gas. For example, water and air. As an aside, you don't actually need the gas. All you need is a liquid exposed to space, whether that's a gas or a vacuum. And when that happens, then your liquid is going to form an interface. Now this interface is actually kind of not related to the interaction between the liquid and the gas, but more just because of the arrangement of the liquid molecules. Okay, so let's actually draw kind of a liquid. Here we've got a liquid, and here's our interface. So here we have a gas or a vacuum. And here inside of our liquid, we've got molecules. There are some that are on the surface and some that are inside of, kind of deep inside the liquid. And so these molecules all pull and push on each other with some sort of cohesive force, right? A liquid has a cohesive force. That's what keeps it together. And so each molecule is kind of in tension in all directions. And if we're deep in the fluid, like these molecules are, kind of like this one right here, he's deep in the fluid and being pulled in every direction by other molecules. And so they all balance out, and this molecule does not have any net force on it. However, the molecules on the outside, like here, are being pulled towards the other molecules on the outside and being pulled towards the molecules inside of the liquid. However, they are not being pulled away from the surface because there's no liquid pulling them that direction. And so you see there's a net imbalance that is pulling, kind of tightening this molecule inwards. And so if you have, say, a lot of molecules on a surface and they're all being pulled inwards, then naturally, if allowed to form any shape, remember, when liquid is exposed to a shear stress, it will deform continuously till it finds a spot where it can be at rest. All right, well, these molecules on the outside are all experiencing a force which results in a shear stress between these layers. And so it will change its shape until it adopts one that allows it to be at peace. So, for example, here's an astronaut on the space station, and he has allowed some water to come out of this pipette that he's holding. And you can see that the water adopts a roughly circular profile. And it does that because here's our drop, here's all of our molecules, and remember, they're all being pulled inwards, and so the most natural way for them to arrange themselves to be in the lowest energy state is so that they're all pointing inwards, and we get a circle or a droplet. Oops. So, because of surface tension, water suspended, in this case in a gas, but lacking gravity, will form itself into a nice circle. Now, if there's a drop on a surface, then you'll notice the water drop will look something like this. And this is because although we have some cohesion between the molecules on the outside, we also have cohesion between the molecules that are touching now a solid interface. And if they are being dragged towards the solid and are attracted to the solid, then they will flatten out. And we will have this, which would be a hydrophilic surface, or a surface that likes water. It wants to be attracted to the water. However, we put a bead of water on a different surface, and now we see that these molecules are here. And the molecules touching this surface are actually rejecting that surface. They don't want to be on that surface because of whatever surface chemistry is happening, such that the water molecules are opposed to touching this surface, often due to an imbalance of surface energies. This is a hydrophobic surface, one that fears water. And so you get the water beating up like you see here, as opposed to flattening out like it does on a hydrophilic surface. So like a non-stick pan covered in Teflon, Teflon is a hydrophobic surface. It doesn't want water to touch it. And so that allows you to cook in a more non-stick fashion. Well, let's move away from this mesmerizing GIF and talk a little bit more about how we measure surface tension. So let's say we've got this little apparatus which has 3 solid walls. Okay, now we have one additional wall which can actually move this way or this way. All right, inside of this kind of square we've created, we're going to put a fluid. And the fluid is suspended between all 4 of these layers and forms a film, a thin film of fluid stretched between all of these layers. Now on the top and on the bottom of this film, we have a fluid that is interfacing with a gas. So we're going to have surface tension. So this entire film is in tension. Surface tension. Now if we wanted to measure that surface tension, what we could do is, since this is in tension, we could pull it. And as we pull it and deform this liquid membrane, we're going to create a net force also pulling this way, exerted by the fluid itself. Okay, and we can balance these forces and find that if we were to hold it still, the force required to hold it against the force due to surface tension exerted by the fluid can be written this way. Y, which is the coefficient of surface tension, is equal to 1/2 times the force required to hold it stationary, in other words, the surface tension force, divided by the length that force is exerted over. Why is there 1/2? It's because we are measuring the surface tension of not 1, but 2 surfaces in tension, right? If we now look at this surface from the side and draw our film, here's our thin film between our walls that we've got here. Well, we actually have 2 surfaces, right? We have the top surface and the bottom surface. Both of those are in tension. So when we do this, we're measuring the tension across the top and the bottom surface, which means we need to divide our answer by 2 to find the surface, the coefficient of surface tension for just the top or the bottom. Okay, so that is the coefficient of surface tension. And that allows us to measure the, strength of surface tension in any fluid. And it will be a function of the material that that surface is touching and what that fluid is made up of. Just as an example, you see here is this is kind of a soap water mixture. So we've got a very thin film stretched between these surfaces and then this kind of circular surface. Now, the person is pulling down, right, exerting a force on this film, and when they let go, you see that there was indeed a tension force, and that tension force exerts an opposite reaction, and it goes until it cannot move this little wire anymore. That wire is then kind of fully extended, and it's once again at rest, although the surface is still in tension. Okay, now what's really interesting about surface tension is that you kind of end up with some curved surfaces. And if there's a curved surface, then there's actually a pressure increase across the interface. So if you have a curved surface that is curved because of surface tension, then you have a pressure increase, which I'll write as delta P, across the interface. And just remember that the higher pressure is on the inside. Okay, and that makes sense, right? If this surface is in tension being pulled, then there's got to be something pushing outwards on that surface to kind of hold it where it is. So as a classic example, we will look at a droplet. Oops. So here is a water droplet which I have cut in half. Oh dear. So let me just kind of visualize for you what we've got. We've got a water droplet, and I've cut it in half. We're looking at this section view. Okay, so we've got this surface tension. So here's an outside surface, and it was in tension. So when we've cut it, there was this force putting this surface in tension. This outside surface, all around this ring. Okay, and so we'll call that the surface tension force. And the force due to surface tension, we wrote earlier, can be found using this equation right here. So let's go back and write that. It's equal to the coefficient of surface tension, and then it's going to be for the length, right? So we had the force due to surface tension. Remember, this was just for measuring using this apparatus, so we won't need the 1/2 here. It really will be the force due to surface tension is the coefficient multiplied by the length over which our surface is exposed. And so our surface is exposed here along this circle because we've cut it there. And so that would be 2 pi r, or the circumference of the circle. That's where our tension is being applied. That's the length along which our force is applied. Okay, now that's counteracted with another force, right? The force kind of on the inside that is holding this bubble, this droplet, that is holding it against this surface tension force that's kind of trying to wrap this bubble up into a tiny space, but it's meeting resistance because of an increased pressure on the inside. So this inside force we can write as the difference in pressure, we'll call it P high minus P low, or delta P, multiplied by the area that the pressure is applied over, or the entire inner area, which would be pi r squared. Okay, so we balance these, say that the surface, oh dear. can't write down there, say that the surface tension force is equal to the inside force because our droplet is not expanding or contracting, it's staying stationary. And plugging them in, we get 2 pi r times the coefficient of surface tension is equal to delta P times P r squared. And we can solve for what that delta P is. It boils down to 2 times the coefficient of surface tension over the radius of the droplet. So that tells us the pressure difference inside of a drop versus outside of a drop. And that makes sense why when you puncture a bubble or anything that's formed a droplet, the internal pressure is now able to overcome the surface tension and it pops. Okay, and it's interesting that as your radius goes down, then your pressure difference actually goes up. So the smaller our bubble, the larger the pressure difference, probably because we have a much smaller curvature. We have to curve our fluid over a much smaller distance, and it therefore takes more pressure to hold our bubble against that surface tension force. All right, well, that's it for surface tension and for module number 1. Thank you for sticking around.